everyone, and welcome to new discussion which we are going to have on active microwave remote sensing. And this discussion I have divided in two parts. So, first we will go through the first part and then of course the next part of the part 2. As you recall our discussion earlier, microwave remote sensing can be divided in two main categories, basically active microwave and passive microwave. So, in active microwave what is done is the energy or pulses are sent by the sensor towards the earth's surface, and whatever the back scattering it collects and record it, and whatever this way we get the data or images and we analyze the data. Whereas in case of passive microwave, it records the natural emission which is occurring in passive microwave. That emission in microwave part of EM spectrum might be very little, but still there are sensors which can record or have been recording. But when we talk about the spatial resolution of passive microwave remote sensing, then the passive resolution has been a big issue. So, you do not get a resolution in meter scale or in meters, but you get in kilometers, maybe 20 kilometer, 15 kilometer or 30 kilometer. And nonetheless, still it can record, because the energy, the amount in passive microwave region is so little that in order to record you need the energy from a large area, and therefore we do not get a high spatial resolution. But in case of active microwave, relatively higher spatial resolutions are possible, and that is being done. So, in this discussion we are going to mainly focus on active microwave remote sensing. Now, as you recall, the EM spectrum in the beginning of this course we have discussed in length, and then microwave part we put as starting from 1 centimeter to 1 meter in wavelength. So, that part of EM spectrum which covers between 1 centimeter to 1 meter or 1000 this 1 centimeter to 1 meter in wavelength, which is considered as microwave, and this encompasses both active and passive. So, for microwave part of EM spectrum, whether it is active or passive, this wave or this wave band remains same, that is 1 centimeter to 1 meter in our remote sensing for remote sensing purposes. Now, a longer wavelength microwave radiation, as you know, can penetrate through cloud cover, haze, dust and all but the heaviest rainfall, as longer wavelengths are not susceptible to atmospheric scattering which affects shorter optical wavelengths. That is a very simple thing which we have also discussed while discussing different laws in remote sensing, and also when we have been discussing about atmospheric effects in remote sensing data. So, if wavelength is shorter, then it will get affected by these atmospheric constituents like water content or haze, dust or anything which is in between satellite and surface of the earth. But when we are having longer wavelength, like in case of microwave, and then it can penetrate, because longer wavelength does not get affected by these small constituents, small size constituent of atmosphere, and like water droplets, tiny water droplets or haze, dust or any other thing. However, if we are having clouds which are really rain bearing clouds or high water content clouds, sometimes they may get affected. And let me give you an example from our day-to-day life. And nowadays most of us have started using disc antenna to receive TV signals, and you might have noticed that whenever there is a heavy rainfall or high dense clouds, black clouds are present in the atmosphere, we do not get signals from the satellites through our antenna to our TV, because the transmission is in microwave region. from these satellites, these geostationary satellites. And therefore, in normal conditions, even when you are having cloud cover but not very heavy clouds or rain bearing clouds or having dust or atmospheric distortions, still we get signals. But whenever we are having such situation, dark cloud, water bearing cloud, dense clouds, then we do not get signals from these satellites through our disk antenna. So, only in that condition it gets affected, otherwise not. Also, these being longer wavelength, microwave radiation being longer in wavelength, can also penetrate through dry sand, and up to few meters, maybe 15, depending on at what depth it encounters the moisture. And if it is completely dry of say 10 or 15 meters, it can penetrate. As soon as it it encounters the moisture or water in subsurface condition, then there is a absorption, and then we do not get, like in case of heavy rainfall, we do not get the signal. So, same way we do not get the backscatter from such areas. And exploiting this kind of property of long wavelength microwave radiation, people have discovered, like in India, old courses of Saraswati river using microwave remote sensing data. So, it plays very important role as a very good way of assessing several things through this active microwave remote sensing. Also passive microwave also having its own applications, which we will be discussing some time later. So, today we would like to focus mainly on the active microwave remote sensing. Now, this penetration property allows us, as I have already mentioned, under almost all weather and almost all weather, not in all weather conditions, exception I have just given, that heaviest rainfall or very dark cloud or water bearing clouds may give problem, and otherwise in almost all weather and environmental conditions, microwave will work. That is why whenever there are problems associated with flooding or some natural disasters where same time you are having cloud cover, people will go and look for microwave remote sensing data, and this is a common thing. So, in flood studies, microwave plays very important role, because during the rainy season when flood occurs, you might be having clouds and all other remote sensing will fail except active microwave remote sensing. So, it plays very important role for various studies, whereas passive microwave remote sensing basically detects the naturally emitted microwave energy, and though this energy is very tiny, very small, and which is related to temperature and moisture properties of the emitting object, soil or rocks or surface within its field of view. So, because the energy is tiny, then you require a large area to cover to register its effects in the sensors, those are which are very far or maybe 850 kilometer away from the earth. So, that is why in passive microwave remote sensing, the data is available at a relatively very coarse resolution. Nonetheless, passive microwave sensors are typically radiometers or scanners, and an antenna is used to detect and record the microwave energy. Now, the passive remote sensing, not passive microwave remote sensing, I am saying simple passive remote sensing, visible infrared and near infrared, their energy is available either through the sun, and that is the reflected energy, or emitted energy in case of thermal channels, and the system or sensors are completely different. Here the sensors are again completely different, even in case of active microwave or passive microwave. So, one has to keep in mind that the sensors or radiometers are completely different than in normal remote sensing, which we call as passive remote sensing. Because of wavelength are long in case of microwave, the energy available is quite small compared to optical wavelengths, and therefore the field of view must be large. The area of coverage per pixel has to be very large, that means coarser resolution to detect energy to record as a signal. This point I have been emphasizing again and again. In active microwave remote sensing, we have reached to up to 30 meter spatial resolution, but in passive microwave we have reached up to 15 kilometer only. So, relatively it is a very coarse resolution data, but it has got its own application. So, because the wavelength is large or long, the energy available is very small compared to optical wavelengths like visible, red or infrared or blue bands, and therefore we require a large area to be covered, which will register as a signal, or that energy which is available will be registered by the radiometer as a signal, and therefore we end up with a coarser spatial resolution data. So, most and so far whatever it has been developed in case of passive microwave sensors are therefore characterized by low spatial resolution because of less energy available. Now, if we quickly we will go through these atmospheric windows, though we have discussed in length about this. The microwave part, if you recall here, it is this part of EM spectrum 1 centimeter to 1 centimeter to 1 meter, and this is the absorbed part which you are seeing here, but large part is not affected by atmosphere, and therefore transmission, because this is what is the transmission is. So, transmission, high transmission is possible, and therefore only in case of heavy rains it gets affected, otherwise it is not affected. And if you see the energy which is available, in visible part the maximum energy is available. This is visible part of EM spectrum. And whereas when we move towards the longer wavelengths, especially in this part of EM spectrum, then hardly energy is available, and therefore it is challenging in case of passive microwave. Now, we come back to active microwave, because there are a lot of satellite, lot of sensors are there in active microwave, and lot of applications, new applications are being developed, especially measuring the deformations induced by an earthquake, landslides, over exploitation of groundwater and many other things. So, in geodesy basically active microwave remote sensing is playing major role, and it is becoming very powerful tool for such kind of studies. So, we will be more focusing on active microwave remote sensing, which provides their own source of microwave radiation to illuminate the target, and that is why it is called active microwave, because the sensor itself will send a pulse towards the earth. So, that is why own source of microwave radiation in microwave part, of course, to illuminate the target, and then whatever is back scattered it is recorded. So, it is two types mainly, one is imaging type and another one is non-imaging. And the most common form of imaging active microwave sensor is radar, that is radio detection and ranging. This is radar is the most common active microwave remote sensing which has been incorporated in many satellites and sensors. So, basically sensor transmits a microwave signal or radio signal towards the target and detect the back scattered portion of that signal. 100% energy will not come back. There will be some changes, some attenuations, some deformations, but nonetheless that is recorded. So, the strength of back scattered signal is measured, because you are having the strength of, you are already having recordings of original strength of the signal which has been sent towards the target, and then you get back the back scattered signal, and if there are changes that can be assessed. So, this is strength of back scattered signal is measured to differentiate or discriminate between a different target, because different objects on the surface of the earth will behave differently with microwave signals, and the time and the delay time, which will create some time delay time between the transmitted and reflected signals or back scattered signal, and which determines the distance, and that is why it is called range. So, the radio detection and ranging. So, the signals are microwave signals, that is the radio signals are sent towards the earth, and then whatever comes back, the delay time is used to detect or measure or estimate the distance which is between sensor and the object, and that is why it is called radio detection and ranging. Ranging means finding the distance by using the time delay factor. So, this is how is in case of airborne radar, or same also in case of satellite based or spaceborne radar, that the signal is first sent towards the target. Here the surface of the earth, many objects are present, say in this one agricultural fields, by water body and others. So, at equal interval, a regular interval, these pulses are sent towards the earth, and then in the blue colors which you are seeing in this photograph or in this image figure is they getting reflected, and we call them as also echo. So, this gets back, and now when if these pulses are hitting water body, the return or back scattered will have a different reaching time or delay time, whereas if it is hitting a built up a building or maybe a land or rock or soil or agricultural land, vegetation will back scatter differently. So, by using this delay in time of reaching these signals, and we can identify different objects on the surface of the earth. And when we study for ground deformations, then in that case single data collection is not sufficient. Then data from between two different dates are used to detect the changes which has occurred, might be due to earthquake, might be due to landslide, might be due to the over exploitation of water, or any other human due to human interventions. So, these changes might be there. This is the basically the nadir height, you can say, or just above the ground. So, this is the ground track of that aircraft or a satellite, and it is looking obliquely. This one has to remember. The sensor, if it say looks downward, then it will not be able to collect the data or back scattering signals. So, it first it sends the signal, as you might have been realizing, in a oblique direction, a slanting direction, and then when the energy is getting back scattered, or these echo signals are going towards the satellite or aircraft, by that time the aircraft will reach. So, by that time it will collect also. So, there are either a large antenna or synthetic antenna, and they are used, means the antenna is synthesized, and therefore, it is possible to collect the data, back scattered data. So, it is looking towards in a slanting range, not vertically downward. So, radar microwave, active microwave remote sensing is not nadir viewing, whereas your simple normal passive remote sensing is generally nadir viewing. Only in case of stereo pairs it looks in side directions or maybe forward backward direction, but in microwave, active microwave remote sensing, it looks in slant direction or oblique direction, we also sometimes call it. So, here the radar, if we see the basics here, radar that is essentially ranging or a distance measuring device, and that is why it is part of also geodesy, that when signal comes here and then these are the pulses which are coming marked here as A, then getting through, then they will hit it, and then back scattered is marked here as C, and then it is collected. So, radar is essentially ranging or distance measuring device. It consists fundamentally of a transmitter which transmits the pulses at regular interval of same strength, because it has to, that is the condition. Otherwise, whatever the back scattered will come, if the original signals are varying in strength, then it will not be useful, that data. So, regularly it transmits the data of same strength. There has to be antenna to collect the back scattered signals, an electronic system to process and record the data, because recording is also equally important. And this transmitter basically, which sends the microwave or radio signals towards the earth, basically generates a successive, as I have said, regular short burst of pulses of microwave, which is in this schematic it is shown as A, at regular intervals. So, you will have a successive such signals which are focused by antenna onto a beam, which is shown here as B. So, by this arrangement we get then back scattered signals. So, radar beam illuminates the surface obliquely. This I have been emphasizing again and again, it is obliquely at a right angle to the motion of the platform. So, if a platform is moving like this, then at right angle of that direction it is sending the signal and collecting the data. Now, the antenna receives a portion of transmitted energy reflected or back scattered energy from various objects within the illuminated beam, and then by measuring the time delay, because after all radar is a this ranging technique. So, there will be some time delay depending on the properties of the objects on the surface. So, by measuring the time delay between transmission of pulse or that signal and the reception of the back scattered echo from different targets, their distance from the radar and their location can be determined. And this ultimately, these signals are processed in a way that ultimately we can create power images like your normal, not really normal, but quite close to the normal images. We will be seeing also examples also very soon. So, as sensor platform moves forward, whether it is airborne or satellite based or space borne, then recording and processing of back scattered signals builds up a two-dimensional image of the surface. So, those signals are recorded in a manner and processed in a way that ultimately we get a two-dimensional raster data or an image of that part of the earth which has been covered by that sensor. As you know that microwave region of the spectrum is quite large, 1 centimeter to 1 meter, and relatively compared to visible and infrared, which are having in micrometers only the bandwidth, and there are several wavelength or bands commonly used in microwave. So, there are various bands are used which we are going to see soon. Now, the penetration, because of these radar waves or radio waves, penetration is the key factor for the selection of wavelength, which band, and the divisions of bands are also little different in microwave part of the EM spectrum. The longer the wavelength and smaller the frequency, the shorter the penetration into vegetation and soil. So, that one has to keep in mind depending on the for what purpose this kind of data or this kind of remote sensing is being employed. Let us see with the different bands and how they are associated with different sensors on board of different satellites. So, in this table we will go one by one. The say P band, that is a part of EM spectrum or microwave part of EM spectrum between 1 centimeter to 1 meter, and here it is roughly located near 65 centimeter. There is a satellite which is called ASR. L band is another, L band is a very common band having a location around 23 centimeter in that spectrum of microwave, and a very popular sensor that is pulsar, ALOS pulsar is there of Japan. JERS SAR also is there having L band. Then S band is there about 10 centimeter and ALMAS 1 is there. And when we see the another very common band is the C band, somewhere around 5 centimeter, maybe sometime you get 5.8 centimeter, 5.6 centimeter, but on average we consider as around 5 centimeter. And the ERS 1 and 2, the synthetic aperture radar sensor were having C band antenna. Radar set also of Canada 1 and 2 both were in the C band. NV set SR, which was very popular, no more now functional, or neither these ERS or radar set including NV set, these are not functional, they all had the C band. RISE set, which is our own Indian remote sensing satellite, and that was also functioning in C band. Then Sentinel 1A and 1B very much functional, and they too uses C band. Now X band also has been used. Again we are going for a less wavelength or shorter wavelength, that is the 3 centimeter, and TerraSAR X1 and Cosmo SkyMed, they uses this band. And then finally the K band, which is about 1.2 centimeter and which is in the military domain. Now, so we as just mentioned earlier that the penetration is the key factor for selection of wavelength. Longer the wavelength, the stronger the penetration into vegetation and soil. So, depending on the applications, these have been designed. The most common one nowadays which we are finding, also ISRO has found, is the C band, which is around 5 centimeter. So, it is a basically you can say is a compromise between shorter microwave wavelength and longer wavelength, and in between you are having 5 centimeter wavelength, that is basically the C band. Now, whichever the wavelength is being used, radar signals can transmit in two that horizontal and vertical electric field vectors, and can also receive in the same way, that means in horizontal, either horizontal or vertical return signals. So, that is another advantage with microwave, that we can have signals either in horizontal and vertical electric field vectors. So, the basically the physical processes responsible for this polarization or like polarized HH and VV return are quasi-specular surface reflection, because the reflection or backscattering coming from different objects of the surface are responsible for this kind of polarization. So, for instance, calm water, if water is standstill water without any waves or any other thing can appear black, that means it is completely absorbing the microwave energy, whereas cross polarized HV or VH return is usually weaker and often associated with different reflections due to, for instance, surface roughness. So, when these sensors are recording data, they are recording in different polarizations, and depending on our applications we can use different polarizations. So, here what basically H, H and V means different polarizations. This is a combination of H and V polarization is that in horizontal the polarization or wave say moving like this, in vertical it is moving in vertical plane. And this is the direction of propagation, this is also the direction of propagation. So, thus there can be 4 combinations between HH, BV, HV and NVH, that there can be 4 combinations of both transmit and receive polarizations as HS for horizontal transmission and horizontal receive, vertical transmission, vertical receiver for HV for horizontal transmit and vertical receive, and a reverse also VH, that is vertical transmit and horizontal receive. So, 4 combinations are possible with these radar data. Of course, everything is now digital. So, digital radar image that each pixel gives a complex number, because it is not simple normal remote sensing. So, the against the pixel it is a complex number, and what this number carries basically, it carries the amplitude and the phase information about the microwave field, which has been backscattered by the scatterers. Scatterers might be rock surfaces, vegetation, building, water body, anything which is present on the surface of the earth will have this kind of backscatter, different backscatter. So, they will have 2 things in this complex number, that is amplitude of that wave and of course the phase information. And the different rows in the image are associated with different azimuth locations, because at different when you go through the microwave images, they are representing different locations in terms of your these signals and direction basically. Azimuth here is for direction. So, different rows of image are associated with different locations, whereas different columns indicate slant range location. So, that has to be kept in mind while seeing or analyzing active microwave data. Here is the geometry and spatial resolution, and this is the slant range which I was mentioning. This is the flight path here, and of course, the ground track is this one, which is just vertically downward. This is the height, altitude of the aircraft or spacecraft. Then the look angle that is there, and this is what is the slant range. If we go, slant range is oblique obviously. When you go on the horizontal plane, then it calls the range. The area which is near is called near range. The area which is far from the slant range are the far range. Then if we measure with the vertical this slant range, then this becomes our incident angle. And of course, as a swath we say in normal remote sensing. So, here also you will have swath width, and that is basically between near range and far range. So, that is main beam, and swath is there. So, main beam is little larger than what we get the swath. As you can see, the blue lines, these blue bands are waving like this. So, this imaging like in these NVSat and other satellites, we are having the imaging geometry arrangement. So, in imaging geometry arrangement, a radar system is different from framing and scanning systems because of these commonly employed for optical remote sensing. This viewing geometry, in this one we will pick a signal and then see what happens after this when it returns back to the satellite. So, starting say here when signals are starting, this is the first signal might have reached there. Now, you are having 9th, 8th, 7th like this, and the first one is here which is coming like this. and then time passes and the signals will, and then you are having back scattered 9, 10, 11, 12, 13. So, these are the basically the return signal from the house, and the vegetation will have different return signals. So, vegetation return signals are different, and see the time difference. When we come in between 6 and 7, it is 11, here it is 7 from the vegetation, whereas in case of house it is 12. So, this will allow us to identify different objects in microwave remote sensing. So, return signals from tree is these ones, whereas return signals from house are different, and the radar pulse from the aircraft which is coming downward from there. So, likewise this is how pulse by pulse the data is sent and then back scattered is recorded, and microwave images are generated, which is the value is a complex number, the unit value. Same thing here, which is we have just discussed, and so the distance is determined from the running time of high frequency transmitted signal and the propagation from the sensor, and the actual range of target from radar is known as the slant range, which we are seeing actual range of target from the radar, and that is the slant range. So, in this case the target is here, and the slant range is the line of sight, distance between the radar and the object illuminated. Line of sight means the direct signals here we are getting, and while ground range, which we have also identified earlier, this is the ground range, that means the vertically downward the track of the sensor, ground track of the sensor, or also here the direction will also matter. So, azimuth is there. So, ground range from that line to the slant range, that is ground range is the horizontal distance between the emitter and its target, and its calculation requires basically knowledge of target's elevation. So, what is the height of the target, that will allow us to find out the ground range. And since the the wave travels to a target and back, the round trip time is divided by 2 in order to obtain the time the wave took and to reach to the target. And there is also, we have seen the depression angle. The depression angle is this, when it is measured with the horizontal at the height of the, at that elevation at which the satellite or aircraft is flying. So, this depression angle is basically will allow us to find out the spatial resolution. So, spatial resolution in both the range, that is the look and direction, and azimuth, that is the flight direction, is determined by the engineering characteristics of the radar system. And the depression angle is defined between angle between a horizontal plane and a beam from the antenna to the target on the ground. And this depression angle is steeper at the near range obviously, and it is going to be shallower at the far range side. And this average depression angle is generally measured for a beam of the middle line of an image strip. So, that is why the target was also fixed in the middle. An incident angle is defined as the angle between a radar beam and a line perpendicular to the surface. So, these are two different angles which are used. Now, how spatial resolution is decided? Spatial resolution in radar images is determined by the dimension of ground resolution or ground area which is covered which is controlled by the combination of range resolution and azimuth resolution. So, here what we are seeing, that in this case this is the range resolution, and here we are having azimuth resolution also. So, this is range resolution, this is azimuth resolution here. So, this further we will be discussing on this microwave, active microwave remote sensing in part 2. For time being, I am going to stop here, and in the next discussion we will continue, especially in the processing part and application part of active microwave remote sensing. So, this brings to end of this particular discussion, part 1 on active microwave remote sensing. Thank you very much.